Swayam Prabha. Digital India. Educated India.
Hello and welcome. This is lecture 5 of the NPTEL video series lectures on CAD. There are certain properties in solids which are invariant under homeomorphic transformations. Today we are going to be studying those. We are further going to delve into topology and solids, invariance of surfaces. There are certain properties that remain invariant under homeomorphic transformations. They are number of boundary components, orientability. I'm going to be talking about orientable and non-orientable surfaces here. Genus. Euler characteristic. This would be an important one. And finally, connectivity number of a surface. First, the number of boundary components. The number of boundary components is represented by an integer c. For a sphere or a torus, there are no boundaries, and therefore c equals 0. For a disk or a hemisphere, recall that hemisphere is a homeomorphic transformation of a disk. The number of boundary components or the number of boundaries is 1, and therefore c equals 1. This figure here is a piece of paper bent into a cylindrical shape. If I start from this point here, traverse leftwards, go down, and then travel rightwards, and go up to the same point, I find that this surface has a single boundary. For this, therefore, c equals 1. For an open-ended cylinder, there would be two boundaries. A circular shaped boundary on the top and a circular shaped boundary at the bottom. For this surface, c equals 2. The next property is orientability of a surface. Consider a sphere here. Imagine that you're standing at point Q with your head pointing upwards. This would represent the normal component at point Q. If you take a closed path and traverse along that path from point Q, and come back, you would find that you're still standing with your head pointing upwards. That means that the direction of the normal would still be pointing upwards. If that is the case, we call this surface an orientable surface. A torus also would be considered an orientable surface. Let me explain this concept to you with a physical example. What I have in my hand is a paperweight. It is not very much like a sphere, but I think it will work as a nice example. Consider this paperweight to be like an earth, and say you're standing somewhere here in the northern hemisphere, say New York. So the pencil represents you, and the tip of the pencil is pointing towards the sky. If you start moving around from this point, go around the world in say 80 days or maybe $8, go anywhere around the world, and if you come back to the same point, your head will still be pointing towards the sky. This is an orientable surface. The next example is of a Mobius strip. Imagine now that you are standing at point Q with your head pointing upwards. You start traveling leftwards, go inside the strip, keep going. Here you're getting below the strip and come back to the same point. What you realize is now that you're standing with your head pointing downwards. In case of a Mobius strip, if you take any point on the surface and if you choose any closed path, it will always happen that when you come back to the same point, the directions of the two normals will be pointing in opposite directions. This is a non-orientable surface. Let me explain this on a physical Mobius strip. This is a paper Mobius strip. Imagine you're a pencil and your head is the tip of the pencil, and you're standing here. Start traveling in one direction. Keep observing the tip of the pencil. If I come back to the same point, the pencil is now pointing downwards. Let's see this again. Once again, the pencil is pointing downwards. Now you can always start from this point here, traverse the strip, come back, not come back to the same point quite yet, pass it, once again travel, and then come back to the same point. You would notice that you're now standing upwards. And you would argue, hey, now you have a closed path that retains the orientation. This argument is okay, but note that concept orientability should be true for every point on the surface and for every closed path chosen. Orientability is represented by epsilon, such that epsilon equals 1 for all orientable surfaces like a sphere, a torus, while epsilon is 0 for all non-orientable ones, such as the Mobius strip. The third property is the genus. It is represented by an integer g, and that is the number of handles for closed orientable surfaces for which epsilon is 1. If you recall this animation, a torus getting transformed into a coffee mug. This is what I mean by a handle. Or genus is equal to the number of cross caps for closed non-orientable surfaces for which the epsilon value is 0. Let's consider a few examples. This is the torus. And this is a doubly connected torus, or a connected sum of two tori. For a torus, the genus value is 1. For a double torus, since there are two handles, each torus can be transformed into a coffee mug. The genus value, or the number of handles, is 2. Question: what do you think would be the genus value for such a solid? The figure looks a little complex to start with, but let me explain. This solid is composed of 5 blocks. Each block has a through hole. And the blocks are attached to each other in such a way that a part of each face of the block is common with that of the contiguous block. So imagine that these are 5 blocks with through holes, all of them attached to each other. Once again, what is the genus value for this? If you consider any block, you can transform it using topological operations like bending, twisting, stretching into a torus. All 5 blocks, therefore, can be transformed into respective tori. Your guess is correct. This solid has 5 handles, and therefore the genus value is 5. Euler characteristic, represented by a Greek letter chi. This is an important property. For polyhedrons, it is given by V minus E plus F. V is the number of vertices in a polyhedron. E is the number of edges in that solid. And F is the number of faces. Let's consider an example of a cube, a block, and a distorted block. We have seen earlier that each of these solids can be homeomorphically transformed into any other via bending, stretching, etc. We all know that these blocks would have 8 vertices, 12 edges, and 6 faces. And therefore, chi would be 8 minus 12 plus 6 equals 2. Let's first test this result and then try to prove it later. For a tetrahedron, the number of vertices are 4, the number of edges are 6, and the number of faces are 4. Chi is 2 for a tetrahedral solid as well. For a soccer ball, for this one in particular, the number of vertices is 60, the number of edges is 90, and the number of faces is 32. Chi, therefore, is 2 for the soccer ball as well. If you notice, this soccer ball has a bunch of hexagons and a few pentagons. The question why can be answered using the concept of Euler characteristic. For surfaces which are not polyhedral surfaces, the Euler characteristic chi is given by 2 minus 2 times g minus c for all orientable surfaces. Recall again that g is the genus value in a solid and c is the number of boundary components. For non-orientable surfaces for which epsilon equals 0, chi is given by 2 minus g minus c. That is 2 minus the genus value minus the number of boundary components. For a sphere, the Euler characteristic will be 2 because the sphere has no genus value and it does not also have any boundary. So G is 0 and C is 0. And we all know that a sphere is homeomorphic to all the figures in the previous slide and in this one. In fact, a sphere is homeomorphic to all polyhedral solids without any holes. Let's now try to prove the Euler characteristic. What I'll do is I'll provide you a pictorial divide and conquer proof using the example of a cube. The proof would be true for any polyhedron which is homeomorphic to a sphere. Here's the cube or a block. For this, we now know that the Euler characteristic is 2. As the number of vertices is 8, the number of edges is 12, and the number of faces is 6. that you're taking this face off. If you do that, the Euler characteristic changes to 1 because the number of faces reduces from 6 to 5. You can also note that this surface now, which is not bounded anymore, is homeomorphic to a disk. And therefore, it can be laid flat on a plane. When you do that, you get a planar graph. This is how. Once again, stretch these edges outward and stretch this face outward to squeeze it flat on a plane like this. This is a planar graph for us. The Euler characteristic, as we noted before, is 1. If I add an edge like this, what I have done is I have increased the E value by 1, and what I have also done is I have divided this face into 2 faces. So effectively, I have increased the F value as well by 1. This is an increase in the number of edges, and this is an increase in the number of faces. Even then, the chi value does not change. I can keep adding these diagonal edges and restore the value of the Euler characteristic still to 1. Let's see how. This is another one, leading to 2 new faces. This is the third one, again dividing this face into 2 parts. This is the fourth one. Well, what I get here is a little skewed face, but that'll work for us. And finally, this edge that divides the bottom plane of the block into 2 faces. You will notice that we have a bunch of triangles now in a planar graph. If you are confused, I'll repeat what I said once again. You start with a cube or a block, take the top face off. We know that that hemispherical surface is homeomorphic to a disk and can be laid flat on a plane. Now, start adding edges such that we start making triangles. Each edge that is added would divide an original face into 2 parts. We do this ensuring that the chi value does not change. I keep adding the edges and keep dividing the quadrilateral faces into triangular ones. Note that while doing so, the value of chi, the Euler characteristic, has always remained 1. The next step now. We carefully remove the edges or vertices one by one. And while doing so, we ensure that V minus E plus F equals 1 is retained. Let's see how. If I let go of this edge, what has happened is there is a decrement in the E value, and the face is also gone. What remains is still a set of triangles. So this removal of edge has not caused any change in this relation. Likewise, if I remove this edge, once again, the chi value remains the same. And I still have a bunch of triangles. Now, if I remove this vertex or this vertex, and the two edges together, there is a decrement of 2 in the E value, a decrement of 1 in the V value, and a decrement of 1 in the F value. Once again, chi equals the number of vertices minus the number of edges plus the number of faces equals 1. I remove this triangle now. Again, the relation is unchanged. I keep on removing the edges and the triangles such that the relation is retained. Please follow this carefully now. Remove an edge, still retain all triangles. Remove an edge, still I have all triangles. Remove a vertex and two edges. Remove a vertex and two edges. And remove a vertex and two edges again. What remains finally is a triangle for which the number of vertices is 3, the number of edges is 3, and the number of faces is 1. So chi equals 1 remains. This is a QED for a pictorial proof for the Euler characteristic. We will now try to relate these two results. Chi equals 2 minus 2 times the number of genus value minus the number of boundary components. This is true for all non-polyhedral solids or smooth solids like a sphere or torus. And chi equals the number of vertices minus the number of edges plus the number of faces is true for all polyhedral solids. Note that this result will be valid if both polyhedral solids are homeomorphic to their corresponding smooth solids. The proof is again pictorial in nature and slightly informal. I'll just give you the concept. Consider this spherical surface, for instance, a smooth surface. Since the smooth surface is homeomorphic to any of the closed polyhedral surface without any holes, the chi value is 2. The first thing you would want to do is triangulate the surface of the sphere to render it the polyhedral approximation. So in a way, what we have now is the polyhedral spherical surface. Clearly, since the two surfaces are homeomorphic to each other, the Euler characteristic remains the same, 2. What we do now is we take off any triangle from the sphere or from the surface. What we have done is we have taken away a face and introduced a boundary component. The number of vertices and the number of edges remain the same. The result, the Euler characteristic decreases by 1 to 1. Let's do this again. Let's introduce another boundary component by taking away another triangle. Here we have ensured that none of the vertices or none of the edges in the two boundary components are common. Once we introduce another boundary component, once again, the number of vertices remain the same, the number of edges remain the same, but the number of faces decreases by 1. Now, the chi value or the Euler characteristic is 0. We can generalize this result. We can keep on adding these boundary components, and we can keep on decrementing the Euler characteristic. In general, chi would be 2, which is the characteristic for a solid surface without any boundaries, minus the number of boundary components, just in case if we happen to introduce boundary contours like these. Clearly, in this case, the C value is 2, and therefore chi is 0. Let's connect the two boundary components now. So this is the first edge connecting the two respective vertices. This is the second edge, and this is the third edge. By connecting these two boundary components via these three edges, we have introduced a through hole in a sphere. When doing so, note that these boundary components are no longer present. They disappear. 3 new edges appear. Two faces from the previous tessellation, they disappear. And 3 new faces appear. So this is the first face. The rear side is the second face. And the right hand side face is the third one. Now let's see how the Euler characteristic changes. The change in the Euler characteristic is the same as the change in the number of vertices minus the change in the number of edges plus the change in the number of faces. There has been no change in the number of vertices, and therefore we have 0 here. The number of edges, they increased by 3, 1, 2, and 3. And the number of faces has effectively increased by 1. Note that these 3 edges have generated 3 faces, and from previous operations, these 2 faces were already gone. So effectively, the increment in the number of faces is 1, and therefore the change in the Euler characteristic is minus 2. The change delta chi is nothing but the Euler characteristic when this through hole is generated. This is also like a handle, because if you think about it, a sphere with a through hole is homeomorphic to a torus. So chi, or the Euler characteristic for this new solid, minus chi for the sphere is equal to minus 2 that we have just observed. This implies that the Euler characteristic for the new solid, which is a sphere with the through hole equals 2 minus 2, which is 0. We can keep performing operations very similar to what we have done here. Keep on introducing new through holes or new handles, and we can see that the result can be generalized. Each time I generate a hole like so, I decrement the Euler characteristic by 2. Effectively, for g number of through holes or for g number of handles that I have introduced, I would decrement the Euler characteristic by 2 times g. This 2 here is the characteristic for a spherical surface or for all polyhedral surfaces which are homeomorphic to a sphere. If we combine this result with that we obtained previously, so this was when we were introducing the number of boundary components on the sphere, we can combine both these results together and we can say that the Euler characteristic chi, which is a function of g and c, equals 2 minus 2 times the number of genus values or the number of handles minus the number of boundary components. Finally, the connectivity number of a surface. The connectivity number is the number of cuts plus 1 made on a surface without separating it into 2 or more parts. These cuts here refer to closed cuts or cuts connecting the points on the boundaries or on previous cuts. Let me explain this on the board. Imagine we have a rectangular piece of paper. This is a closed cut. This is a cut that joins any 2 points on the boundary. And this is a cut that joins a point on the previous cut with that on the boundary. For closed surfaces, the connectivity number is given by 3 minus its Euler characteristic. For a surface with boundaries, like a disk for example, the connectivity number is given by 2 minus the Euler characteristic. Let this be an exercise for you to find as to how the connectivity number is related to the Euler characteristic. A surface with connectivity number 1, 2, or 3 is called simply, doubly, or triply connected, respectively. A sphere is simply connected. Back to the paperweight example. I can take any point, sketch a closed path around it, and cut the surface along that path. So a single closed path would make me separate this paperweight into two pieces. And hence, this paperweight, or equivalently a sphere, is simply connected. A torus is triply connected. Let's see how. The first cut would give us a cylinder. This is the first closed cut that gives us an open cylinder. The second cut gives us a plane. And the third cut would separate this plane into two parts. Manifolds. This is the final concept in the lecture. Manifolds refer to local shapes describing the local topology of geometric entities. For a curve, the local topology is a line, and that's the reason why a curve is called one manifold. For a non-intersecting surface, the local topology is an Euclidean plane, and that's the reason why a surface is called a two-manifold. A surface is two-manifold if and only if at point P on the surface there exists an open ball B of a sufficiently small radius r such that the intersection of the ball with the surface is homeomorphic to an open disk. Let's try to understand this statement via a few examples. So if you remember what an open ball is, it's a collection of all the points within the ball and not on the surface of it. Consider a sphere, for example. Take an open ball, intersect it with the surface of the sphere, and the result of that intersection would be an open disk. Likewise, again, take an open ball, intersect it with a toroidal surface, and that intersection result will be an open disk. They are therefore two-manifold or manifold solids, in short. Consider this example here. This is like two cubes sharing a common edge with each other. At any other point on this solid, if you take an open ball and intersect it with any plane, you'll get to see an open disk. But if you place that open ball on this edge, the result of the intersection will be two intertwined disks. So this vertical disk here is the result of an intersection between the ball and this vertical plane, and the horizontal disk here is the result of intersection of the ball and this horizontal plane. So the two disks are intertwined like how my hand looks. I cannot separate the two disks unless I tear one of them off. So here, the solid is a non-two-manifold, or in short, a non-manifold solid. Of course, if you recall the homogeneous three-dimensionality property of valid solids, this solid here defies that property. We conclude this lecture by having an inquisitive mind pose this question: what are different ways in which solids can be represented? We'll cover this in the following lecture.